everybody. So for our senior design project, we redesigned a movable bridge, which is located in Duluth, Minnesota. My name is Brenna Jones. I'm a mechanical engineering major, and Alana and Mickey are both civil engineering majors. So the problem with the initial bridge that is located in Duluth, Minnesota, is that it was constantly needing to be repaired because it was breaking all the time, which is mostly due to the mechanism. So it previously had a pulley system in place, where the cables would snap often, or they would slip out of the grooves, which was obviously not good since pedestrians would not be able to cross the bridge. So this bridge is necessary to Duluth because it connects Canal Park, which is the entertainment and shopping district in Duluth, the Duluth Convention Center, and it's a half-mile walk around the slip. They can't fill in the slip because that is where the historical boat is stored, and as well as the tour boats sit there as well. So as I was saying, this bridge had a lot of issues, the main ones being the mechanical failure of the pulley system, but it also had issues with the control box, and it would also get stuck in the open position during extreme weather, extreme wind conditions, which is often because it is off of Lake Superior. They also did not take into account the bridge weight or the deck weight of the bridge in their initial design. And so 3 days after they opened it in 1991, they had to close it for repairs since it broke and counterweights. So by the time, so they built the bridge in 1991, and by the time 2008 had hit, they had spent over $1 million in repairs when the initial bridge was only $800,000. So affectionately called the Little Blue Bridge that never worked.
Some considerations that we took into account when determining our scope of work were that the local and tourist communities really like the current aesthetic of the bridge. So the three main things we decided were to keep the arch truss design as it is so that they still have that aesthetic that they enjoy, to have a similar lifting mechanism appearance. So the structure is the same, but the mechanism that's moving the structure is different. And then to keep the length of the bridge the same due to a tour boat and a historical boat. So the span is currently a 150-foot slip, but the span itself is only at 75 feet. This is an image of the historical boat that they have to take out for some maintenance and repairs. And when they do that, there's only 7 inches of clearance on either side, which is a pretty close call. So making the 75-foot span smaller isn't an option. Some of our initial design concepts we looked at were different movable bridge options. We were really just trying to verify that the double leaf bridge was what we wanted to go with, since we wanted to keep that same aesthetic. So another one we looked at was a vertical lift, which is that middle image you see there. And it's just wasn't correct for this project because it needs to be as tall as the largest ship you're gonna try to remove. Pretty tall to have to move a 75-foot pedestrian bridge. A transporter, which isn't pictured here, again, similar reasons that it would need to be as tall as the largest ship you're going to remove, which just isn't feasible for our project. And then finally, the swing and pivot bridge, which is that final image there on the right-hand side in the bottom. You can see it has a structure, or it has a support in the center that supports all of the mechanical components, which, seeing our last slide, isn't feasible because the boat needs to be able to go through the whole opening. So that's just how we verified that the double leaf vascular bridge was.
And then for our foundation design, we reached out to a geotechnical engineer that works here at the university as an adjunct to both ask his recommendations and if he had any connections in the Duluth area. And both the connection and recommended piling. So from our connection in Duluth, he recommended driven steel piles into bedrock, and then in Duluth there is a glacial till layer in some parts that acts as a bedrock for heavy loads. For lighter loads, we could use a steel screw pile. Another type of pile is a cast-in-place concrete pile, but based on our preliminary research, the usable depth of that is just shy of the bedrock, so we opted not to use that. And type of foundation is a shallow foundation, which erodes very easily. And as you saw, this is right next to water, so there would be a high chance for it to erode and become unstable. So we opted against that. And then how piles work is there's two main types, a friction pile and an pile. So the end-bearing pile, otherwise known as a point load pile, essentially acts as a stilt. So all of your weight is transferred down into that bedrock or a very dense soil layer, such as the glacial till. And the friction element holds the through that frictional force. And for the bridge, we opted for the longer piles to get down into that very stable material that exists in Duluth.
So our other final major that we had to make was for the mechanism. So our options were to either go with the pulley system, which would have to either be fixed or modified so it wasn't being broken all the time. Otherwise, our other options that we looked into were using a rack and pinion, which I'll go over briefly. But in this slide here, the initial mechanism can be seen on the right-hand side of the top corner. And as you can see, the cables cross a lot, and it's complicated. It takes a long time for them to be able to fix it when it breaks. And then in the bottom right picture, there's just a diagram of how it operates. There are two motors which drives belts, and that turns the axle, which then spools the pulley. We want similar for the other mechanism when we decided to choose that. So this just goes a little bit more in depth on what a rack and pinion, the advantages of using a rack and pinion and a roller and pinion compared to the pulley system are. So as I said before, the pulley system is complicated, caused a lot of issues and needed a lot of repairs, but it was initially cheap. And that is why we assume that they went with that design in the first place in 1991. But as you can tell, as I said, by 2008, they'd spent over $1 million in repairs. It obviously was not a good choice as it wasn't able to be maintained. The rack and pinion is a lot safer than the pulley, as it does not, there's less chance of it slipping and falling. It has very little maintenance compared to the pulley system. The difference between a roller and the roller and pinion and the rack and pinion can be seen in the pictures. The top one is the rack and pinion and the bottom one, the roller and pinion. So the roller and pinion is a little different than the rack and pinion, but it offers advantages of minimal slippage, fatigue, noise, and backlash, and has even less maintenance than the rack and pinion. So for our final designs, we go into a little more in depth into what our initial design. And so as you can see, this is the initial structure that existed. As we said before, we want to make sure that it looks very similar to how the bridge was before. So we're keeping all of the same structural basis of it and having it rotate around the same axis of rotation. And as you can see in this animation, you can see where the axis of rotation is, and the motor drives it to lift it with the hinges and the having a connection point between those two. And this just shows what the roller and pinion would look like in our system. And so it uses two racks and then two rollers, and it is secured at the top with a plate which has the roller secured inside of it, and so as the motor moves, it will drive the rack through it. And these are just more detailed drawings of those separated so you can see a little more in depth how they look, and then just some detailed dimensions.
So next is our CAD drawing of just the bridge itself. And so we're talking to our advisors for this course, and we determined that the best way to look at the structure would be to just analyze half of it. So we just analyzed it as like a cantilever structure so that it could support itself. So the first loading consideration we looked at was the wind loading that would act on it in its vertical position. So after our loading calculations of the wind, the diagram we came up with to show the load or the wind that would be acting on each leaf itself when it's in its vertical position. After that, we needed to determine the beam sections. We did that by using the tributary areas of the beams. As you can see in the purple highlighted rectangles, that's that each beam would be in charge of. After that, we determined that there are 3 different beam type 1s and 2 beam type 2s. The type 1 is the blue, type 2 is the red. We just found that they had different tributary areas that they're in charge of, so they would be smaller sized beams. In the end, sketch of it, so we knew that we needed 3 type 1, 2 type 2, and then those large girder beams to support those. With that, we had our distributed loads acting on our beam type 1. We found a factored load for beam type 1 to be 4.129 kips per foot, and for beam type 2, it was 2.53 kips. After we got those beam size, then we were able to go into the girders. The only difference between the girder loading is it becomes a point load when we were analyzing it. So we have 3 of the point load 2, which is 33.24 kips, and then 2 of the point load 1 of 20.392 kips acting on that large girder. With these loadings, we were able to calculate the maximum moment, and we selected our beams using the steel manual that we got from our steel design course last year. And then once we selected those beams that you can see on the right-hand side, we checked that the moment capacity is greater than our calculated moment beam, which said they were good beams. With that, we were able to calculate the weight of the bridge by taking the beam selection multiplied by the quantity and the length of the beam, and then summing them up to get 36.47 kips for the total weight of our whole bridge. The final thing to look at for our bridge was the deflection. So we looked at the LRFD deformation requirements and found that for this span, it could be 0.075 inches, and our deflection calculation ended up being 0.024 inches for our structure.
So then loads that Mickey calculated along with the weight of the bridge, Brenna was able to calculate the required motors to actually complete that lifting motion. So she determined that 2 motors for each side at 15 horsepower and RPM would be sufficient to complete that motion safely. And we also used that loading for our pile calculations. So for our foundation considerations, we learned from our contact in Duluth that there are 3 soil above that bedrock that we talked about earlier. So first is urban fill, which is just anything that has been touched by people, which is categorized as a medium to loose sand. Then alluvial sand, which has been deposited by running water, such as a river, which is categorized as a loose sand. Lacustrine clay, which has been deposited by a stagnant water, such as an old lake bed, which is a soft clay, and then that glacial till or bedrock layer, depending where you are. And then if you can move on, my words will change. So then we talked about that skin friction earlier. So although we are opting to do a point load pile, skin friction does still play a factor, but due to the depth of the water, we opted to neglect the friction from that first layer just because it's the exact same depth as that layer. So we neglected it. And then based on from the Principles of Foundation Engineering textbook, we determined that 4 H14 by 73 piles are required to support this bridge. So that is 2 per side, and that would be 1 under each girder. So then very quickly, some of the complications that we had with this project is we originally started as a team of 4, but unfortunately our other mechanical team member withdrew from the course. So everyone appreciate how much Brenna got done this semester. We also had great difficulty finding the original bridge documentation to even reference what needed to change so that we didn't make the same mistakes. And then it was also very difficult to find specific soil information for the area. So I ended up combining things from our textbook, the Minnesota USGS, the Minnesota DNR to come up with something in the realm of realism to get that estimate. our last thing was just a little miscommunication regarding the initial structural design. So thank you for your attention. Are there any questions we can answer for you?
We do have time for questions.
Yes, Dr. Pilling.
Did you guys do any kind of cost analysis with this? Like how much would it cost to build that? I know you said in the previous one it was 800,000 that they spent in
Yeah.
1991 and then an extra million later.
So we're not actually finished with our cost analysis, but we're putting in the report for this project. But we've been working on it. So
Do you have any kind of like maybe estimate?
not right now.
Ballpark? Okay.
I don't recall the Minnesota DOT estimate off the top of my head, no.
Okay.
In the beginning, you guys said like that's the blue bridge that doesn't work. Up or down all the time if it doesn't work.
It stays down most of the time. It only opens when a ship needs to go through it, a boat needs to go through it,
Yeah.
which is not as often as people cross over.
I think there was one time where it was that it got stuck open due to wind. So the wind was blowing too extremely that they couldn't safely lower it without it like snapping. But as Brenna said, it does typically get stuck down.
That obviously the line flow is going to be the pedestrian road for that value. Like, how did you determine the pedestrian road, like the line?
I'll defer to Nikki.
We did a really safe estimation of, we weren't able to find how many people could fit on the bridge, so we did an estimation of how many people could fit on the bridge, multiplied by the average weight of an American on our bridge, acting on our bridge.
And then if I recall correctly, did you like do research of like busy times during the summer to like kind of get the foot traffic in that area?
Yeah, we found like on average, I mean, I can't remember the number off the top of my head, but we found on average how many people use the bridge a day, but that didn't really tell us how many people are actively standing on the bridge at once. So we just did a rough estimate of how many people we thought could fit on the bridge with the size of bridge it was.
So basically you kind of estimate the line flow and then you have the dead load, which is the self-weight structure itself, right?
Bridge deck, because the original plans forgot to account for the bridge deck is one of the issues that they had.
Okay.
So we made sure to put that in our dead load.
And then we factor with the load combination too.
Mhm.
Okay, so can you go back to that that girder, there's a girder that you show with the
This one?
Yeah, okay, so
Yeah.
this one is, so you basically, basically you have a girder with a whole bunch of points. And so when you do your, so those two low, lows right there,
Mm-hmm.
is that like, those are a lot heavier than the two side low, right?
Yeah.
Okay. So when you do your deflection, did you, find a specific case that would have a deflection for this? Because I don't think in the steel manual there's a case for that.
Yeah, we just did the deflection at the end, since we analyzed it as a cantilever beam.
Okay, so you,
I think we have time for one more question.
Where did you get the idea for this?
Brenna really likes the Blue Bridge in Duluth.
Okay.
Yeah.
There you go.